So I'm Jikin Lau, and I'm a postdoc here at Texas A&M University. And today I'm going to talk about some comparisons between the two platforms that we've heard about today. So the PolyMapper and Poly QTL R platform, and the Map Poly and QTL Poly like pipeline. And so kind of a little bit background. So I just finished my PhD last year, and I worked on tetraploid garden roses. And with that, I began to use a bunch of these programs, and I'm going to talk about it a little bit later, but I kind of mix and matched pipelines because at that time, only certain ones were available. And so we'll get to that in a second. Kind of a caveat before we get into this talk is that I'm not a developer, and I may not know all the tips and tricks of the software. And everything that I've learned is basically from the vignettes and from the manuals of these software. So there may be new things that Peter and Marcelo have already put in or things that they've already fixed that I'm not aware of. So a quick outline is I'm going to give a quick comparison between the linkage mapping software. Then going to talk about the QTL mapping software. And with those, I'm going to talk about the pros and the cons and the ease of use of each software and use case scenario of the software. And then I will kind of end with a real empirical data set on tetraploid rose. So looking first at the linkage mapping comparisons. For both the software, they both can take discrete dosages and genotypic probabilities, and you can get those as discussed earlier today in the other talks. You can get that from GBS or from Array. And just one big difference that's actually mentioned in, I believe, the PolyMapper vignette is that because your discrete dosages, as seen in this up here, it's just one number per marker per individual, and the input file for these are much smaller than genotypic probabilities, which gives a probability of each dosage. So those files will be a lot larger because there's a line for every marker and sample combination, and also there's probabilities associated with every single dosage. Another thing is that y'all have heard about today is the ability to input VCF files. I know a lot of y'all work on GBS data and get VCF files. And right now, to my knowledge, I don't believe PolyMapper is able to input VCF files. However, there is a workaround. You can use MapPoly to input the VCF files, and then you can output a dosage matrix using the export data to PolyMapper function inside of MapPoly that will give you a dosage matrix that you can use to map inside of PolyMapper if you wanted to go that route. So some quick linkage mapping basics. For any linkage mapping software, you need to be able to estimate your combination fractions. You need to somehow be able to group your markers into linkage groups, and then you need to be able to order your markers in each linkage group. And both of these software take slightly different approaches. PolyMapper first estimates the recombination fractions between all the simplex nulliplex markers first, and with that, it establishes a scaffold of linkage groups and homolog groups. And then from there, it estimates the recombination fractions between all the other marker types compared to this scaffold, and it adds those markers to the scaffold. And then it orders the markers using MDS, or multidimensional scaling, utilizing MDS map from the Hackett group. And we heard about that earlier this morning. Map Poly takes a slightly different approach. It estimates the recombination fractions between all marker types, and then it can establish linkage groups using a few different ways. You can use UPGMA, which is a clustering algorithm, and that uses the recombination fractions to cluster your groups. You can use the genomic information. If your markers have the genomic information, you can cluster using that. Or you can use an intersection, as Marcelo showed earlier this morning. Then the map order is estimated using a hidden Markov model or HMM chain. And the HMM chain implemented in Map Poly requires a priori order, which can either be an MDS order that you provide for it to run the chain on, or you can use a genomic physical order if your markers have that data associated with it. So there may be a couple different strategies. Depending on what crop you work on, you may have a reference genome available, you may not. And say, for instance, if you had a reference genome available, what could you do? You could use Polymapper, and you can group using recombination fractions. And to my knowledge, I may be wrong. I guess Peter can correct me later if I'm wrong. I don't believe there is a way to group by the genomic information in Polymapper. With Map Poly, you can use the genome information to group your groups and then do your map ordering like we talked about earlier. The other strategy is, okay, what if you don't have a reference genome, or what if your reference genome is pretty poor? What would you do? Well, you would have to use either Polymapper and group using the recombination fractions, or you would have to use Map Poly and group using UPGMA clustering of the recombination fractions. So kind of talking about the advantages and disadvantages of both platforms. And this is from just a user perspective, or I guess more of a user / breeder perspective. So what I found was that Polymapper gives the user a little bit more control in chromosome groupings when you're looking at the recombination fractions. Sometimes when you are trying to group your simplex nulliplex markers, you can with your eyes see the groupings. You can see the however many groups. You can see your chromosomes group out. However, they may be at different lods. And with Polymapper, you can kind of almost hack the program and kind of go in and manually assign groups. And that's one advantage that I saw there. Also, MDS map is a faster ordering algorithm. And then the disadvantages of Polymapper, I feel like, are that it's more hands-on and it's requires longer scripts. And I believe in the Q&A session above, Peter had mentioned that if he were to make some improvements, he would make some things a little bit more automatic. So kind of an example of what I mean by longer scripts is for the map that I'm going to show later, it took around 1,200 or 1,300 lines of code to get my map, just because I had to do, the data was pretty messy and I had to remove certain groups and go back and forth and do a lot of steps over and over again. And I think the last disadvantage may be that there's no way to group using the genomic information from the reference genome. And again, that might be incorrect, but from what I know about Polymapper, that's what I think, unless there is something that's hidden that can do that. Looking at Map Poly, the advantages are that it is more automatic, and this means that your scripts that for your mapping is a lot shorter. And kind of give you a comparison, a minute ago we said that the Polymapper map took around 1,200 to 1,300 lines of code. Well, the same map that I did in Map Poly took around 250 lines of code. And another advantage is that Map Poly, when you give it a VCF file, it retains the genotypic nucleotide call for the markers, and it doesn't just give you a A/B kind of dosage output. Your maps actually will tell you what nucleotide you have, or deletion, or whatever the marker type is. And a disadvantage of some disadvantages of Map Poly are that I've found that it's been really computationally intensive, and that's due to the part that you need to make all the pairwise recombination fraction comparisons between all marker types at the very beginning. However, discussed earlier, Gabriel has been making some changes and trying to implement things to use less memory to estimate all the pairwise recombination fraction calculations. And I've actually tried that, and it is a lot faster and uses a lot less RAM. And then another disadvantage, I don't know if it's really a disadvantage, but the marker ordering using the HMM chain is a lot slower than MDS maps. So kind of give you an example, the same map in Polymapper probably would take an afternoon, and I can run and get a map. But in Map Poly, if I use the same very similar filtering steps, the HMM chain can take up to 1 or 2 days to finish, just depending on how many markers are on each chromosome. But I'm sure that will be improved, and they will be faster ordering in the future. So kind of looking at the empirical data set, what I was talking about earlier, what I did was I had a biparental mapping population of 200 individuals, and it was mapped with both mapping software. And kind of the filtering that I did was less than 1% missing data across markers. About 7.5% missing data was allowed across individuals. And just note that this was using the row SNP array. So looking at some map statistics, this is the number of markers that were placed on the map. And what you see here are 3 maps. In the yellow is a Polymapper map. In the red is a Map Poly using the physical order as for the HMM chain. And then the blue is using Map Poly using MDS as the for the HMM chain. And what we can see from this slide is that pretty much all 3 ways to map this map, you get about the same number of markers placed on the map, around 4,500 markers. Polymapper has a little bit more at 48. Looking at map size, typically we want smaller map sizes in linkage map, and that typically means that a smaller map size typically means you have less genotypic error. However, what we see here is that Polymapper has the smallest map size, and Map Poly, the physical one, has a smaller than the MDS one. And there is a note here that this can actually be adjusted in Map Poly depending on how much global error you assign after you make your maps. There's a step where you can assign a global error, and right now these are at 5%. If you move that up to 10%, then these maps will be shrunk and more markers will be thrown away. Looking at average gap size, actually these next 3 slides will look like one mapping software performs way better than the other, but you'll see in about 3 slides an explanation of why we see such stark differences. So Polymapper looks like it has an average gap size of 0.13, and Map Poly between 0.38 and 0.5 centimorgans. And looking at the largest gap size, you see the same thing. Polymapper has a smaller, largest gap size. And looking at unique positions, it looks like Polymapper has a lot more unique positions compared to Map Poly. And this next slide is where we will see what explains all these bar charts that we just looked at. I know this is kind of a really messy slide, but this is just one of the linkage groups. This is a linkage group 1. And down here, you have the Polymapper map. You have Map Poly using MDS and Map Poly using the physical order. Right down here, you have your maps that are in centimorgans. And what you see is that on the Polymapper map, there are a lot of markers placed really close to each other. And that's a function of, that's just what happens when you map with MDS map. Whereas when looking at the examples using the HMM chain, what happens is that the HMM chain realizes that, oh, really close markers are actually, they can't only be really just 0.1 or 0.2 centimorgans off of each other, that they're actually right on top of each other, and that they are linked. So this is what results in the gaps and the larger average gap sizes and the larger overall gap sizes. And what you see up here are the homologs. And one thing to notice is the homologs up here are not in, they're equidistant from each other, and they are in the order of the map. So what you can see is that from looking at the homolog maps, that it looks like the Polymapper maps are a little bit more sparse towards the ends of the chromosome. And that's just another, I guess, feature or another thing that happens in MDS map. The ends are a little bit more bare. Another interesting thing that I saw from this output is that if you look up here, the colors or the dots represents the doses. So in Polymapper, you don't really see, you just see doses of 1 and 2, and then sometimes 3. And why you see that is in Polymapper, very early on, you turn all your marker types into the most simple segregating types. So all your 3s and 4s, I guess triplex, but quadruplex gets turned into simplex, nulliplex, and so on and so forth. They get converted to the most simple segregation types, and that's why you see that. Looking at this is just the map files, their output. This is just a text representation of what you saw in the slide earlier, where Polymapper has a lot of markers that are really close to each other, whereas in the Map Poly maps, you have a lot of markers that are overlapping and that they're right on top of each other. Looking at this next slide, this is just showing the colinearity between the different maps. And what we see is that there is really high correlation between the maps. You see a few markers that are misplaced, but generally pretty high colinearity. So moving along to QTL mapping, we looked at Poly QTLR versus QTL Poly, and some requirements for QTL mapping, as discussed earlier this morning, is that you need phase linkage maps and you need genotypic probabilities or IBD probabilities. And one really nice thing about these two, I guess, pipelines are that they kind of talk to each other. The developers have been really good about talking to each other so that one data input type can be exported out to another type, and so on and so forth. So kind of this is where I want to talk about my work in my PhD, because whenever about 2 or 3 years ago, whenever I got my genotypic data back, only PolyMapper was available for mapping. So I did my maps, and when I got done with my maps, I had my phenotypic data, but at that point, Poly QTLR had not been released, and only QTL Poly had been released. So what I had to do was I took the phase maps from PolyMapper. You had to input them into Map Poly to make to calculate your genotypic probabilities, which then were input into QTL Poly to do your QTL scans. But what that was for my PhD work, and what I'll show in a bit on the QTL scans are direct using the pipelines directly as they were intended to be. So some key differences for the two platforms are that PolyQTLR uses an additive effect interval QTL mapping method, and each trait needs to be examined separately. So again, kind of like the mapping counterpart, the scripts are a little bit longer because you have to look at each trait separately, examining them for where the peaks are, the PVE, the allelic effects, etc. Some of the steps, like mentioned earlier, can be done automatically now, like including markers as cofactors and looking for other markers, or keeping the one peak as a cofactor and then looking for other QTL. That has been automated. And the differences in QTL Poly is that it uses a random effect multiple interval mapping method, which was discussed earlier today, where it has a forward significance and a backward significance where it adds and subtracts QTLs. And it automatically scans, Gabriel showed you on the demo, it automatically scans all the traits in a phenotypic file, and it keeps those in a structured output. So there's some key differences. So looking at an example, this was part of my dissertation work, and we looked at black spot over 2 years over 2 locations, and we took these phenotypic black spot severity scores monthly, and that resulted in about 18 environments, and that had a narrow sense of about 0.2 and a broad sense heritability about 0.8. So using QTL Poly, this is very similar to what you saw earlier this morning. When you run it, it first finds a huge peak on 5, then finds a peak on 1, and then during the refining step, it decides, oh, the 1-on-1 is not significant, and from the outputs of QTL Poly, the position of this QTL was at 61 centimorgans. The estimated H2 is how they kind of estimate PVE. So this is a heritability of this QTL. It was estimated to be about 0.5. And then in the output of QTL Poly, you see allele estimates. So if a individual had this broad-eyes F allele, it's estimated to have a negative 0.4 effect. And just the interesting thing, after you do all your QTL scans here, you can go back and look at your genotypic probabilities and actually your homolog probabilities, and isolate your individuals that carry this F allele. And when I went back and did that, I found 94 individuals that carry this F allele at this QTL. Looking at PolyQTLR, you see a very similar scan. However, PolyQTLR said that both the QTL on 1 and the one on 5 were significant. What you see in the black is kind of a first scan, and what you see in the red is taking this as this QTL on 5 as a cofactor, which makes this a little bit more significant. And using PolyQTLR to estimate the PVE using a 1 QTL model, it's about 13% for the 1-on-1 and almost 40% for the 1-on-5. using a 2 QTL model, it's about almost 49% for both of the QTL. And this is how poly QTLR displays its allele effect. And what you see is that it's a allele. So H1 through H4 is from SW, and which is stormy weather, and H5 through H8 is from BE or bright eyes. And again, you see that it's a simplex, nullplex inherited trait on 5. The 1-on-1 is a little bit more messy, which it is right here is where the QTL is. So it's a H1, H4, H7, and H8 that lower the amount of black spot you see in the field. So that's a little bit messier up here. And same thing in poly QTLR, you're able to go fish out the individuals that carry the allele. And to kind of make an apples to apples comparison, I'm only going to look at the QTL on 5. So I went in and tried to fish out all the individuals that carry the H5 allele. And again, we found 94 individuals that carry this H5 allele. Now, an interesting thing is that when I went to go look at the intersect of the 94 from QTL Poly and the intersect between the Poly QTLR and 94, they agreed on 91. So there were 3. So there was 91 individuals that agreed from both. And this next slide kind of shows on the left here, these are individuals that Poly QTLR said was significant. Oh, that's that. This on the left, right? The 3 individuals that Poly QTLR had said that carried the, I guess, the resistant allele, but the QTL Poly did not. And on the left is the same thing. This is what QTL Poly had said carried the allele, but the Poly QTLR did not say it had the individual did not have the allele. And what's interesting to note here is that it's where all the recombination breaks are. So if you remember earlier, we're looking at, well, I'll go up 2 slides. For the QTL Poly, we're looking for the F allele on linkage group 5 at the line. So coming back here, you're looking for individuals that carry this blue haplotype. And what you see is the red line is where the QTL is, and it's basically where the recombination breaks are. And same thing over here. For the poly QTLR, we're looking for H5 allele, and then you see the same thing, that H5 is where the breaks are. So in summary, PolyMapper and PolyQTL are in general more hands-on, and they have more user input and more scripting, and I believe is more useful if you want to tinker a little bit more, or if you want to explore a QTL more. And Map Poly and QTL Poly in general are more automatic, and they require less user input, and the result, the scripting of those, it takes a lot fewer lines of code to script for those. So it's kind of up to the user and your use case scenario, which analysis pipeline to use. Or you could be like me in my PhD work, where I kind of mix and matched. And it is nice that they can go back and forth, because there are functions in each one that the other ones don't have, that you can kind of input a map made in one pipeline and go look at figures made in the other, and vice versa. And almost as a last slide, I want to show you that we also ran DiQTL on the same population, but we actually had 2 populations that were interconnected, and this is the same QTL on 5 that popped up. There's one on 3, but it comes from another parent, and I wasn't talking about that in the QTL comparisons.